Hello students, in this video let us learn about the contribution of the scientist Kepler. So you might be familiar with Kepler's laws. Kepler was an astronomer who lived in the 16th and 17th century, and he was a contemporary of Galileo and a proponent of heliocentric theory. By thoroughly studying various astronomical observations, especially that of Tycho Brahe, one of the famous astronomical observer, he put forward various laws, 3 laws that summarized the working of this heliocentric model. So in this class, we will look into the Kepler's laws and try to understand the basic features of them. So the first law of Kepler's laws is that all planets move around the Sun in elliptical orbits, with the Sun at one of the foci. So as we know, since then, scientists and astronomers try to put forward circular orbits for planets because of the aesthetic beauty relating to circle. But now, in Kepler's law, we first see an elliptical orbit being proposed, with Sun being at one of the foci. So as you can see here, the planet moves around in elliptical orbits. Sun is at one of the foci. Then there will be one point that is very close to Sun, and this point is called perihelion. Similarly, there will be one point that is farthest from the Sun, and that point is called aphelion. And this kind of orbit, this kind of elliptical orbit actually goes well with the Newton's laws and the inverse square law of gravity. Now moving on to the second law of Kepler. According to the second law, while moving around the Sun, a line connecting the Sun and the planets sweeps equal area in equal time. Or in other words, aerial velocity of the planets remains a constant. So as indicated in this figure, if we draw a line from the Sun up to the planet, this line will sweep equal areas in equal time, meaning that aerial velocity is a constant. So as you can see here, when a planet is very close to Sun, the line is shorter. So if more area or an equal area is to be swept, planet will have to move faster. So here this time period T4 minus T3, in this time period the planets moves a much longer distance. Similarly, if it is at the aphelion point, near to the aphelion point, this line is very lengthy and the area swept will be constant only if it moves little lesser. So as a result, its velocity will be smaller at the aphelion point. Or we can see that the angular velocity. Here you can see this angle is much smaller than this angle, right? So near the perihelion point, the angular velocity will be larger, and near to the aphelion point, when the planet is at the aphelion point, its angular velocity will be lower. Either way, aerial velocity is constant. So keep the relation or the difference between aerial velocity and angular velocity in your mind. Angular velocity varies according to position. Planet will sweep different angles in different time, in the same time when it is at different position. But the aerial velocity will be constant. The total area swept by these lines is always a constant. Now moving on to the third law. According to third law of Kepler, in the case of planets, cube of the semi-major axis of the elliptical orbit is proportional to the square of the period. So I can write a cube is proportional to t square. A is the length of the semi-major axis and t is the time period. So let us see a picture. So here you can see an elliptical orbit. Sun is at one of the foci. Major axis is the largest distance that you can draw inside an ellipse. So semi-major axis is half the distance of the major axis. So this is A. This much distance is A. T is the time period for one complete rotation around the sun. So if a planet starts from here A, in how much time it will return up to A. That is denoted by time period T. So Kepler showed that A cube is proportional to T square. The time period of the planet has a relation to the length of the or the width of the size of the elliptical orbit that it follows. So we can actually prove this Kepler's third law using Newton's law of gravity. We know that when a planet orbits around the sun, the necessary centripetal force is actually provided by gravitational force. So if any body is moving in a circular orbit or is moving under a central force, the central force or the centripetal force is to be provided by something. In the case of planets orbiting around the sun, the centripetal force is gravitational force. So what is gravitational force? According to Newton's law of gravity, gravitational force F is equal to Gmm by r square. Here G is the gravitational constant, m is the mass of the sun, small m is the mass of the planet, capital R is the average distance from planet to the sun. So we know the centripetal force. Equation for the centripetal force is given by Fc equal to mv square by r, mv square by r, or which is equal to m omega square r. We know omega is equal to p by r, right? So from this equation, if you substitute here, centripetal force is m omega square r. So since these forces balances, since the centripetal force is provided by the gravitational force, I can write centripetal force is equal to Fg. So here m omega square r is equal to G mm by r square. So you can see this small m will cancel out, and here for omega, we know omega and time period are related as omega equal to 2 pi by t. So instead of omega, let me write 2 pi by t the whole square into r cube. I took this r square to the left hand side. This is equal to Gm, or simply Gm multiplied by t square by 4 pi square. So Gm into t square by 4 pi square is equal to r cube, isn't it? So you can simply state that r cube is proportional to t square. So if we consider this r as the average distance from sun to earth, then it will be approximately equal to the semi-major axis A. So this theorem simply implies that A cube is equal to t square, or r cube is equal to t square. So Kepler's third law very much agrees with the Newton's law of gravity and our concept about centripetal force being provided by the sun. And these are so this equation, we have actually proved this third law in the context of circular orbits. If it is in the case of an elliptical orbit, this radius should be replaced by semi-major axis A. So in this class, we have seen the three laws of Kepler, where he beautifully outlines the basic functioning of planetary motion. And earlier, after many centuries, all these laws still holds good. All these laws are correct. And we can see that there is a huge shift in the perspectives and scientific achievements when we come to the 15th, 16th and 17th century. So Kepler contributed greatly by providing a beautiful formulation for how the planets orbits around the sun. I hope these laws are clear for you. Thank you.